Великий космический крузер. Будет это через 9 лет? Конечно, нет. Нам не нужен. Okay? We don't need imperial star destroyers to take us to Mars. We just need systems that can send packages to Mars capable of supporting a small group of people and sending either those or comparable packages back. Okay. So I'll stick with English. We need heavy lift boosters. Now, for a while now, that seemed like an obstacle, but we're getting them again. We had them half a century ago. Saturn V, you see here, taking astronauts to the moon. Now we have Falcon Heavy. It's got about half the capability of a Saturn V, but it's 3/4 reusable. NASA is about to have the Space Launch System with 3/4 the capability of the Saturn V, about 1/4 reusable. And SpaceX will soon have the rocket that they currently call the BFR, which will have equal capability of the Saturn V and be fully reusable. So we will have this in much less than 10 years. We will have this within 4 years. Okay. Now, if you have this, how can you do a mission to Mars? Okay. You can fly to Mars every 26 months, roughly every 2 years. So in the first month of flight operations, we launch one of these heavy lift boosters, and we use an upper stage to throw to Mars an automated payload of about 40 metric tons. This flies to Mars on a minimum energy trajectory, takes 8 months to get to Mars. When it gets to Mars, it deploys an aeroshield to make friction against the Martian atmosphere, and that captures it into Mars orbit. And then after we check it out and check out the weather and make sure that things are the way they should be, we take it deeper into the atmosphere, and we use the aeroshield to plow us down to subsonic speeds. And then we pop a parachute, come down slow, and finally put ourselves down softly on the surface of Mars using rockets, just like we did with the Viking mission in 1976. Or we did it in a somewhat different style with the Curiosity mission in 2012. Okay. Now, what is this payload that we have landed on Mars? It consists of a number of things. The primary object is the Earth Return Vehicle. Okay. This is a small rocket ship. It's got a diameter of about 5 meters at the upper stage here. Okay, this one. All right, here we go. This is the crew cabin, 5 meters in diameter, about 6 meters tall, so it's got 2 decks, each with 3 meters of height. And then we have 2 methane, oxygen, chemical rocket stages here, which, however, are unfueled. Must be unfueled, or this would weigh 5 times as much as it does, be much too heavy for a rocket of Saturn V type capability to send to Mars. However, in some of the lower stage tanks that are later going to contain methane, we have about 6 tons of liquid hydrogen. And then slung below the vehicle, not shown in this diagram, we have a light truck with like a little pickup truck with a little nuclear reactor, маленький ядерный reactor, in the back of the truck with a power of 100 kilowatts. Now, after it is landed, the truck is telerobotically driven a couple of 100 meters away from the landing site, unwinding a cable off of it as it goes, and then the reactor is put on the ground, preferably in a depression like a little crater. and then the reactor is turned on, and now we have power at the ship. And what we do then is we run a pump, and we suck in the Martian atmosphere, which is mostly 95% carbon dioxide gas, CO2. Okay? CO2 can be reacted with hydrogen in the presence of a catalyst to produce methane and water. This is 19th century chemistry used in the gaslight era. Methane, that's good fuel. That's the gas you may use in your home to cook. The water is then electrolyzed. It is split into hydrogen and oxygen. The oxygen is the oxidizer to burn the methane. It is stored in oxygen tanks. The methane is stored in methane tanks. And the hydrogen is recycled to make more methane and water, and it goes. And then finally, to get more oxygen, which is needed to get the right mixture proportions of oxygen and methane for the rocket, we have an additional reaction, which we split carbon dioxide into carbon monoxide and oxygen. The oxygen we keep as our oxidizer. The carbon monoxide we vent as waste. You can do that on Mars. There are no environmental protection authorities there. And so what you've done is at the end of this process is you've taken 6 tons of hydrogen, you've combined it with 102 tons of CO2 to make 108 tons of methane oxygen rocket propellant. And so that is a leverage of 18 to 1. It's like a pioneer going out into the wilderness, and instead of bringing his food, he brings a rifle and some ammunition, and he can acquire the useful mass of bison and deer and elk and all of this to feed himself. Okay? And that's the key to successful exploration. Travel light, live off the land. Okay? A successful explorer makes use of the materials that are available in the environment they intend to operate in. Okay? When on Mars, do as the Martians will do. Okay? Will the Martians import their fuel and oxygen from Earth? No, they will not. They will make it there. So that's what we must do starting on the very first mission. Now, in fact, the leverage here is so large that of the 108 tons of useful propellant produced, we only need 96 for the Earth return vehicle. There's 12 tons left over that we can use to power ground vehicles using chemical engines, which are much more powerful than you can get with electric cars. And this is very important because why are we going to Mars? We're going to Mars to explore. What's the primary requirement for effective exploration? Mobility. So this gives you that kind of mobility. And this is very important because the idea is that being able to use local resources is not only the key to making the mission cheap, it's the key to making the mission effective, which is equally important because there's no point going to Mars unless you can do something useful when you get there. Okay. All right. So it took 8 months to fly to Mars. It took 10 months to make the propellant. That's 18 months. There's 26 months, to be precise, between launch windows from Earth to Mars. So long before the next launch window has opened up in the 3rd year of operations, okay, we will know that we have a fully fueled Earth return vehicle waiting for us on Mars. So there's no question in this plan about the crew being stranded because the propellant production didn't work. It already has done its job before they ever launch from Earth. Okay. So, but that being the case, in year 3, we launch 2 more rockets. One sends another Earth return vehicle fuel factory with no one in it. The other sends a habitat spacecraft with a crew of 4 astronauts in it. Okay. Now, because our return ride is waiting for us on the surface of Mars, we don't need to fly to Mars in an Imperial Star Destroyer. We don't need to fly to Mars in a comparatively modest Millennium Falcon. No, we can fly to Mars in a tuna can. Now, this tuna can is somewhat larger than the one that you get at the market. It is 8 meters in diameter and 6 meters tall. So once again, 2 decks, each with 3 meters of height. Okay. The lower deck is more of a cargo hold, workshop kind of place. The upper deck is where the crew actually lives. Here's one potential layout for the upper deck of the HAB. What you see are 4 little staterooms for each of the 4 astronauts, a science area, exercise area, a kitchen, galley area, and in the center here is a solar flare storm shelter. It's worth talking about for a minute. There are 2 kinds of radiation that can harm you in interplanetary space. There's solar flares and cosmic rays. Solar flares come from the sun. They come unpredictably. Typically, average frequency about 1 big one a year, but you could have 2 big ones inside of the same season and then nothing for 2 years. But it could come anytime, but probability is about 1 big one a year. Okay? And they come with a big flood of radiation, okay, that can deliver thousands of REMs, tens of sieverts of radiation, which is enough to kill, over the course of a few hours, which is enough to kill an astronaut, either immediately or after a fairly brief period of radiation sickness. That's the bad news. The good news is that the kind of radiation that solar flares are composed of are protons with energies of about 1 million volts. And those can be stopped by 12 centimeters of water, or other things that from the nuclear point of view are essentially water, such as food, or things that water and food become as the mission proceeds. And we have enough on board the ship to pack it in around a limited central area and make a shelter. And if a solar flare happens, the alarm rings, the crew goes in here, and they're stuck in there pretty tight for a few hours until it ends, and then they come out. And this will happen once, perhaps twice in the course of the whole mission. And that is how you are safe against the solar flare. The other kind of radiation are cosmic rays. They don't come from the sun. It's not even clear where they do come from. But the particles come in from interstellar space into our solar system, and they have energies not of 1 million volts for every particle, but 1 billion volts. That is 1,000 times more energy for each particle as a solar flare particle. So you can't stop that with 12 centimeters of water. It would take meters of water to stop that, and we don't have enough mass available for that purpose. So we're going to take that dose. That's the bad news. The good news is that the magnitude of that dose is not that big. It's only around 50 rem, half a sievert, for every year you're in interplanetary space. And we're going to be in space for a year on this mission. 6 months out, 6 months back. We're going to be on Mars for a year and a half, but there we have shielding. We have Mars underneath us, and we can put sandbags on the roof of the HAB. We can shield there. So we're going to get our 50 rem. What is 50 rem? What does it mean? What that means, 50 rem scattered over an extended period like this, is about a 1% chance that you will get a fatal cancer sometime later in your life, assuming there is no advance in medicine. Now, if you're an average person who does not smoke, you have a 20% chance that you're going to die of cancer. This would make it 21. If you're an average smoker, it's 40. So in fact, if we recruited the crew out of smokers and sent them to Mars without their tobacco, we would be significantly reducing their chance of getting cancer. So one reason to send people to Mars could be for their health. Okay. Now, I want to say one other point here. Because there are people who are yelling and screaming about we have to solve the problem of radiation, or we have to achieve 1-month transits to Mars before we can go because of the radiation danger. This is counterfactual, because in fact, there have been about a dozen astronauts and cosmonauts, and here are their names, who have spent enough time in space at the space station or the Mir where they have gotten cosmic ray doses comparable to that which they would have gotten going to Mars and back. And there have been no radiological casualties among this group, okay? You want to go talk to them, okay? And you wouldn't expect it, because if you've got 10 people and they each have a 1% chance of a casualty, you would expect no casualties, and there haven't been. But there is something in space that has caused harm to astronauts, and it is zero gravity, okay? Zero gravity, extended exposure weakens your bones and muscles. Now you can survive it, the astronauts on the space station do, but they come back weak in bone, weak in muscle. We don't want that because we're going to Mars to explore, and that involves hiking around in a spacesuit. It's a physical activity. So I believe the proper way to go to Mars is using artificial gravity. And we can create that by, here's the spacecraft, here's the upper stage that threw it to Mars. We extend a tether between them. It's 1.5 kilometers long. If we spin this at 1 RPM, it will create Mars gravity in the HAB. If we spin it at a little less than 2 RPM, it will create Earth gravity in the HAB. And that is how we avoid the deleterious effects of long-duration exposure to zero gravity. And I believe that it's frankly irresponsible that neither the US nor the Soviet space program did any serious research into artificial gravity, not a single artificial gravity satellite except for one Soviet one in 1977 with some mice. Okay, we need to be researching this now. All right, so they're going to Mars on a 6-month trajectory. It doesn't take that much extra fuel to get to Mars in 6 months. In fact, the InSight probe that NASA launched this year was launched in May, and it's going to arrive in November. That is a 6-month transit that can easily be achieved, okay? And so the crew will go on a 6-month transit. If you try to go much faster, then it really starts reducing your payload, and we don't want to do that. The extra speed is not worth the loss in redundancy of spacecraft systems. You're actually less safe if you do that. So we go on a 6-month trajectory, which nevertheless does get us there before the Earth return vehicle, which is on an 8-month trajectory. We get close to Mars. When we get there, we fire a pyrotechnic device. It cuts this cable, and then we aerobrake into Mars orbit, and then we proceed to land at landing site number 1, where the fully fueled Earth return vehicle is waiting for us. Now, we've been on the ground there with Marsochads for 2 years. We have thoroughly explored the area, taking photographs of everything. The crew is completely familiar with the area. There is a radar beacon on the ground to draw them in. We have an expert pilot flying the HAB. We should be able to land right on the spot, okay? And some of you may remember during the Apollo program, or you may have read, that during Apollo, we landed an Apollo lunar lander within 200 meters of a Surveyor robotic spacecraft that had been put there before. We have much better guidance systems today. So we should be able to do this. But let's say we don't. Let's say we land 10 kilometers away from the landing site, 20, 50, that would be a huge landing area. We're still okay, because we have with us in the lower deck of the HAB a pressurized ground rover, about like a little SUV. It has a one-way range of 1,000 kilometers running on methane oxygen. Okay, if you can't land within that distance, you have no business being a pilot. But let's say they don't even do that. Let's say they land on the wrong side of the planet. That would represent a very serious problem with the pilot selection process at Johnson Space Center. Okay. If that happened, okay, we can still save the mission because we got the second Earth return vehicle following us out to Mars. If they land on the wrong side of the planet, they bring them down to them where they are. Okay. And now in that case, you would be depending upon the propellant production working while you're there, but it's already been proven by the first one, and you have a human crew on the scene to help it along, although you'd want to keep the pilot out of it in this case. And there you go. And then finally, as a fourth level backup on the mission, if you can't land correctly, if you can't drive there, if you can't use the second Earth return vehicle, the fourth level backup is we have the whole crew on Mars where they have natural gravity, where they have substantial radiation protection from the Martian environment, and they have enough supplies with them to last for 3 years. So if worse comes to worse, they can just tough it out on the surface of Mars until more supplies and another Earth return vehicle can be delivered at that time. So now, but if it works correctly, then we can land the other Earth return vehicle anywhere we want. We could land it right next door. We could land it on the other side of the planet. I would like to land it myself a couple of 100 kilometers away because it will define the next place we go, and we'd like to explore somewhere new, but I'd like it to be within at least one-way driving range of the ground transportation. Now, so it goes there to set up the next landing, which will go there in year 5, along with another Earth return vehicle, which is their backup, but which otherwise opens up landing site number 3. So the plan is 2 launches every 2 years. That's an average of 1 per year to support a continuous program of Mars exploration. Now, when we were flying the shuttle program and it was going properly, we were flying an average of 6 per year. So we're talking an average of 1/6 of our heavy lift capability to support this. That means we could do a moon program in parallel, we could do asteroids in parallel, we could launch great big telescopes in parallel. We don't have to stop the whole space program just to do Mars, and we can do those other things and still do Mars. Okay. This is an actual photograph of the Mars base. Well, not precisely, but nevertheless, this will allow you to see things that have not yet been seen. Okay, here's the Earth return vehicle, here is the HAB module, here is the reactor in the crater in the background that provided the power to make the propellant, which is made in a machine that's in the landing stage that acts as the takeoff pad for the rest of this. Here's some solar panels, which are backup power for the reactor. Here's the exploration vehicle, little pressurized rover. Probably can't see it that well, but the light truck that was used to deploy the reactor is a backup vehicle is over here. This thing is an experimental greenhouse. It's not mission critical. It's an experiment in learning how to grow crops on Mars in Martian soil, Martian water, Martian gravity, Martian sunlight for the benefit of future missions and future bases. So we're going to be on Mars for 1.5 years. Why 1.5 years? Well, that's how long the planets have got to move around before you get your launch window back to Earth. So that's the plan. 6 months out, 6 months back, 1.5 years there. There is an alternative plan that can be done. It's known as the opposition class mission for various historic reasons. And that spends 2 years in space on unequal legs and only 1 month at Mars. So that actually, instead of 2.5 years, is about 2.1 years. So if your goal is minimum time away from Earth, that's the plan. But that's not the right goal. If your goal is minimum time away from Earth, don't leave. Okay? The goal should be to explore Mars. And so you want a mission like this. It spends 60% of the mission time on Mars, not 5%. Okay? Because that's the useful part of the mission. And also, this plan actually has lower exposure to cosmic radiation because it spends less time in space. Now, we're on Mars for 1.5 years, and what are we going to do? We're going to explore for all kinds of stuff, but there's 2 questions that make Mars of interest not just to professional scientists who want to get papers published so they can get tenure. And these 2, but of interest to you, all of humanity. The first set of questions is there life on Mars? Okay. This is a real photograph of Mars and taken by Viking in 1976. And what you can see here, look at this, these are water erosion features on the surface of Mars. And since then, we have discovered many, many, many water erosion features, dried up lakes, even a dried up ocean on the size of the Mediterranean Sea on Mars. And in fact, just this year, we discovered an underground lake of liquid water on Mars. using ground-penetrating radar. And there's probably a lot more of those lakes, because if there's one, there'd be hundreds. And so what does this mean? This means that Mars was once a planet that was warm enough for liquid water. It's all frozen now, except for the underground stuff. Okay. And in fact, the early Mars was very similar to the early Earth. We're like twins that were identical or very similar at birth, but then went off in different directions with different kinds of careers. And so life evolved on Earth in 200 million years. Mars was warm and wet for a lot longer than 200 million years. So if the theory is correct that life evolves naturally wherever you have the right physical and chemical conditions, then life should have appeared on Earth. And if we can go to Mars and find even fossils of that past life on the surface of Mars, let alone living organisms underground in those underground lakes, because those could support life still. If we find any evidence of this kind, it would prove that life is a general phenomenon in the universe. And since we now know, as we just heard, that there are planets everywhere, and every star has a correct distance where you have the habitable zone, where you have the right temperature for liquid water, whether it's near or far, depends on the size of the star. Okay, so if there's planets everywhere, and there's decent planets everywhere, and if life evolves wherever it has a decent planet, life is everywhere. And since the whole history of life on Earth is one of development from one of simple forms to more complex forms, manifesting ever greater capacities for activity and intelligence and ever more rapid evolution, if life is everywhere, it means intelligence is everywhere. It means we're not alone. This is something that thinking men and women have wondered about for thousands of years. It's worth finding out, and we can find it out by exploring Mars. Now, at the end of a year and a half on Mars, we get in the Earth return vehicle, we start it up, okay, and you fly home. You leave behind on Mars all this other stuff. You leave behind the hab, the reactor, the greenhouse, the vehicles, the solar panels. Is that bad, leaving all this very expensive aerospace hardware behind on Mars? Shouldn't we bring it home? No, we have a lot of stuff here already. The idea of Mars missions is to bring as much stuff to Mars as you can and come back with as little as you can, because everything you leave on Mars is available for future explorers to use. And after a number of missions have occurred, the circles here, this is a map of Mars. Texas is here for scale. And you can see Mars is, in fact, much bigger than Texas. Okay, this would be an area about the size of Ukraine. The landings proposed are at the centers of these circles. The centers are within driving distance of each other, and each landing could explore one of these territories. But after we do a number of these landings, we'll have explored a lot of territory, and we'll have the answer to this question of whether there was life on Mars, whether there still is life on Mars, what is its biochemistry, does it use the same genetic alphabet that all Earth life does, or does it use a completely different alphabet? You know, all Earth life uses DNA and RNA, which is, by the way, Latin letters, just like the English alphabet. But as you may have heard, on Earth we have other alphabets than the Latin alphabet. You know, so, I mean, there's the Chinese alphabet, the Japanese alphabet. I hear about there's some alphabet around here that people use that's different than the English alphabet. So maybe they use the Cyrillic alphabet for their genetic code. Okay, not RNA and DNA, but something else. Okay, in other words, is life as we know it what life is, or is it just one example of life? Drawn from a much vaster set of possibilities. All right, we'll know the answer. And then the question will be moved to the second point on the agenda, which is not was there or is there life on Mars, but will there be life on Mars? Because the most important thing to know about Mars is that it's not just an object of scientific inquiry. It is that. It's an important one. But it's more than that. It's a world. It's a planet with a surface area equal to all the continents of the Earth put together that has on it all the materials needed to support life and therefore technological civilization. And if we can go to Mars and learn how to turn those materials into resources, then we can make Mars habitable. Now, what do I mean by make Mars habitable? Do I mean terraform the planet, you know, like in Star Trek II, The Wrath of Khan, where they take this barren world and they turn it into this wonderful planet with forests and meadows and flowers and chipmunks and birds and flying fish? Are we going to do that? Yes, that's what I mean, okay? I have faith that we will do that to Mars someday. Why? Because we are life, and it is the nature of life to take barren environments and transform them into places that are friendly for the development and propagation of life. That is the entire history of life on Earth in a nutshell. You know, life has changed the Earth. Life put oxygen in the Earth's atmosphere. Oxygen is an artifact of life. Life created the soil on the continents. And symbiotic communities of plants and animals have colonized the continent, starting from the seashore, up the plains, up the hills, up the mountains. As high as life can go, it goes. And no sooner does any barren place appear on the Earth. You know, think of Hawaii coming out of the Pacific Ocean. Well, Hawaii is a great place now, but it wasn't when it came out of the ocean. Okay, life transformed it. Okay, life put plants there. Life put animals there. Life put nice hotels there, okay? All these things were done by life, and it would be unnatural if humans, as the kind of bird, as it were, that is capable of flying across the ocean of space to barren islands out there and bringing the seeds of life, did not do that. So we're going to do that someday. But that's not what we are going to do. We who are in this room today. No, that is beyond our time. But what we can do is transform Mars, make it habitable in a different sense, by transforming it not so much physically as intellectually. Because what defines whether an environment is habitable or not is not only a function of its objective nature. It is a function of your skills. It is a function of whether you know how to take the materials there and turn them into resources. Two people can be stranded in a forest. One could starve to death in 3 weeks. The other could live there forever in comfort, because to one, the resources are invisible, and to the other, they are apparent. It's the same with Mars. We go to Mars, we start landing HABs in one place, we make it into a real base where we can do engineering research, and we start developing the skills that make materials into resources. Mars Direct starts making fuel and oxygen. We go beyond that. We learn how to grow crops on Mars. We learn how to make concrete on Mars, and ceramics and bricks and glass and plastics and metals and wires and tubes and habitation structures. We develop that set of skills, then Mars becomes habitable for us. It becomes a place where human civilizations can be founded and sustain themselves and grow so much that in the fullness of time, they become big enough and strong enough with enough industrial capabilities and technological capabilities that they can actually address the question of physically transforming Mars. And so the goal of the program is not just to bring life to Mars, it's to bring Mars to life, okay? And from there, it's on to the stars. I ja думаю, что мы можем делать это вместе. Спасибо.
Victor Panchenko, former NASA Ames Research Center. So, first of all, thank you for hypothesizing about the origin of life on Mars could be based on Ukrainian alphabet. I think it's great. Jokes are difficult, I think, in here. Okay. Second, I'm surprised you didn't address the problem of perchlorides that are known to be, in abundance on Mars surface, and as you know, they are at the levels that are currently about 1 million times more than allowed by FDA standards. So, what are your thoughts about addressing that harmful chemicals that could be found on Mars, besides the perchlorides and stuff like that?
So,
thank you.
I didn't quite catch the word. You're referring to toxic chemicals as opposed to... Oh,
perchlorides.
Oh, yeah, sure.
A lot of people concerned about
it. Which are also present in detergents. Well, look, you want to keep Martian dust out of your hab, okay? And not just for chemical reasons, but because the dust can impair the operations of equipments and all of that. In terms of creating greenhouse soil, you'll have to wash it. A lot of the peroxides on Mars are actually destroyed on contact with water. So you're going to have to detoxify the soil, wash it, in order to make it usable to grow plants. Next question.
Давайте. Вон там, да, молодой человек руку поднял. Так, вот.
Hello, thank you very much for your presentation. I've been to your lecture on Monday here in Kiev, and I asked you a question, why aren't we doing this right now? And you said that there are a lot of problems like political issues, and there is no unification around one idea. And I want to ask you today, how do you think what we as people of the Earth can do to make this happen? Thank you.
What we can do to make it happen is to do it. You know, this breakthrough in entrepreneurial space initiatives has really opened up the field, not only for private individuals in the United States, but in other countries. In fact, here in Ukraine, you have a very active startup called Firefly, which is developing a low-cost rocket that will launch microsatellites, which are a coming thing because with the reduction of the mass of electronics, it's now possible to build satellites that weigh 10 kilograms that previously took 1,000 kilograms to do. And you could launch constellations of these things, and they could both be used to improve life on Earth with communications, but also establish communications and navigation systems on Mars. I think, frankly, Ukraine could be a major player in this because you have a large contingent of highly skilled engineers that well, they may not be too happy about this, but they're willing to work at salaries about 1/5 of what it costs to hire an American engineer. And if you can eliminate institutional barriers to investment in starting businesses, you can have hundreds of space businesses started here, either by domestic capital or outside capital, and be a major player in this. Because this is not just about creating big launch vehicles. That's part of it. It's about creating life support systems, communication systems, instruments, remote sensing instruments, in situ instruments, systems for making propellant out of local materials. There's all sorts of things that can be developed that do not require billion-dollar investments to get going and develop businesses around. And I think it's my hope that some people here in Ukraine will really take the initiative, in particular on the business leadership front, in pulling together teams of engineers and others, and then raising some capital and identifying a niche where you can produce a high-tech product that could be used by this program and participate in it. I think there's a massive opportunity here. There are several reasons to go to Mars. Now, we're talking the near-term benefits. Okay, yes, there's the answers to these incredible scientific questions. Then there's also the impact that it will have on society. I believe that human societies are like individuals. We grow when we challenge ourselves. We stagnate when we do not. A Humans to Mars program will be a tremendous stimulation to the development of intellectual capital of every country that participates. In the United States, in the 1960s, the number of science graduates doubled at every level, high school, college, PhD, and in some areas it tripled, okay? And I was one of them. I was one of the children of Sputnik and Apollo, okay? I'm unusual in my generation in that I actually went into the space business, okay? But the rest of them went off and invented computers in Silicon Valley and created vast amounts of wealth by doing that, far exceeding the cost of the Apollo program. We've been benefiting from that ever since, okay? And, you know, youth loves adventure. Humans to Mars is an invitation to adventure to every young person. Learn your science, you can be a pioneer and explorer of new worlds. Out of that, you get millions of scientists and engineers and inventors and doctors and medical researchers and technological entrepreneurs. Okay, that's a benefit that vastly dwarfs the cost of any such program. Now, beyond this, you're asking a different question, which is how can a Mars colony? No, it's conceivable that governments could establish a Mars base and run it at a cost. They do that right now with McMurdo Sound in Antarctica. But how could a Martian civilization actually develop? Okay, what can it export to pay for its imports? You don't want to be entirely autarkic. That's the road to poverty. Okay, now you do want to be self-sufficient in things that are simple and heavy and can be readily made on Mars. You want to make your oxygen, you want to extract local water, you want to grow crops, you want to make steel. That can be made on Mars quite readily. But what about importing computer chips and things that are much more sophisticated? You're going to have to pay for them, even though your cost to do that is reduced because they're small, they're lightweight, you don't need that much launch to do it. Well, what's the export from a Martian colony? Will it be, you know, deuterium? Because, I mean, Mars does have 6 times as much deuterium for every hydrogen as Earth does. Well, maybe. But I think that the most probable export from Mars is not any material object at all, but intellectual property. Because what you're going to have on Mars, in a Mars colony, is a group of technologically skilled people in a frontier environment that they're going to be forced to innovate and free to innovate. They're not going to have any patience whatsoever with institutional obstacles to invention. For example, they're going to be using greenhouses for agriculture that limit crop area. They have to clean the soil before they can use it. So they're going to want crops that have absolutely maximum yield per square meter. They're going to use genetic engineering to do that. And they'll have no patience for people who run around and say, but what if the big tomatoes get loose in the habitat and start killing people? No, they're just going to do it. Okay, they're going to have an extremely pragmatic attitude. This, by the way, was characteristic of 19th century America. It's going to be tenfold more prevalent on Mars. Okay, this attitude of, this is a better way, let's just do it, even though this is not how it's been done before. And there's going to be nothing in rarer, in greater demand on Mars than human labor power and skill sets. So they're going to make innovations in robotics and artificial intelligence to augment the number of workers and increase the diversity of skills that are available within a limited population. And maybe they'll develop fusion power because there is deuterium on Mars and they don't have competing energy sources like fossil fuels that are readily available on Earth. So they're going to make all sorts of inventions. Mars is going to be a pressure cooker for invention, and those inventions can be patented on Earth and licensed on Earth and make billions of dollars that can be used to pay for Martian imports at the same time that they greatly advance life on Earth. Okay? You know, America's a very inventive country. That, I think, has been among its greatest contributions to the world, that we made all these inventions which then went worldwide, you know, including things like electric lights and laptop computers and iPhones and aeroplanes and all this. Okay, well, Mars will be a nation of inventors for sure. And I think that's how it will make the money to finance its growth, and I think that's how it will benefit the Earth.